let's move on a bit to a new subtopic, kinetic molecular theory. In this video, I will briefly remind you about kinetic energy, and then we will discuss kinetic molecular theory. You'll need to be able to discuss how temperature and kinetic energy are related, and how the molecular distribution of speeds exists. And finally, use aspects of the kinetic molecular theory to explain the ideal gas relationships. Let's quickly remember what kinetic energy is. It is the energy of motion. The faster an object goes, the more kinetic energy that it has. Specifically, it is related to the velocity by the equation of 1/2 mv squared. Now let's talk about the kinetic molecular theory of gas. You'll recognize a lot of these from the ideal gas law. First, we know that molecules are point masses. This is the same as what we talked about before. Molecules have a mass, but they have no volume. We of course know that this isn't true in reality, but it is an assumption made in the equations for the kinetic molecular theory. We also have constant random motion occurring with completely elastic collisions. Again, identical to what we talked about in the ideal gas law section. And finally, molecules are neither attracted nor repelled, or in other words, there is no interaction between the molecules. And lastly, our new concept for this slide. The average kinetic energy is proportional to temperature. Now let's take a little bit closer look at that last part. Now let's think about what this means. If kinetic energy is proportional to temperature, then that means that if we have two different gas samples, but they are at the same temperature, then they must have the same kinetic energy. Now let's look one more time at the kinetic energy equation. We have 1/2 mv squared. If the kinetic energy for two different gases are the same, what does that mean has to be true about the relationship of the masses and the velocities? At a given temperature, if the kinetic energy is the same for the two gases, this means that the molecule with the larger mass must have the smaller velocity in order to have the same kinetic energy. Take a moment and go back to the simulation and see this for yourself. Until now, I just told you to play with one of the gases, but now you can play with both the heavier and the lighter gas and notice the differences in the speeds. We have discussed pressure as a general concept, but there is also a very specific reason why pressure acts like it does. The molecules collide with the container, and this is what creates pressure against the walls. Now, thinking in terms of molecules colliding with the walls, what would create an increase in pressure? Let's start simple. If we want the pressure to rise, should we hit the walls with more force or less force? More force, of course. So if we want more total force on the walls, we can do this in two ways. First, we can get each molecule to hit with more force. The second way is if we aren't having the molecules, each individual molecule, hit with more force, we can simply put more molecules in the container so the overall force on the walls will be greater. That way, even if the force isn't higher, there are more hitting the walls, and so the total amount of force goes up. Let's talk about how each of these relate to the ideal gas law. As the molecules hit the wall with more force, the kinetic energy must be increasing. Remember that temperature and kinetic energy are proportional. Therefore, as temperature increases, pressure increases. That's Charles' law. The other way to increase pressure is to increase the frequency of the collisions in the area. This can be done in two ways. Either by having more molecules in the area so each area gets hit more often, or by decreasing the area. The former means that as N increases, so does P, or as the number of moles increases, so does P. That's Avogadro's law. The other means that a decrease in volume increases the pressure, and that's Boyle's law. Now, I snuck in a new idea into that last equation. Notice that instead of V, I had a U with a line over it. We should take a closer look at that now. The U with the line over it is the root mean square speed. Think back or revisit the simulation that I sent to you earlier. Were all of the balls moving at the same speed? Definitely not. You can follow each one and see that some move slowly, some move quickly, and some change their speeds. The U with a line over it denotes a way of putting this into a kinetic energy formula. Let's look at distributions and their relationships to temperature and mass now. Though before we do this, we need to do a moment of graphical skills just to make sure that we're on the same page with the graphs that we're going to be covering. Let's answer some questions about this fake grade distribution that I've put up for you. Why? Why would we do this in a chemistry video? Well, because students tend to mess up distribution graphs, and they have a hard time understanding them. But they do intuitively get grade distributions. And so we're going to answer the questions on this first, and then when we move to the question on speed distributions, it's going to seem much more simple than if we jumped straight there. Now let's look at this. What is the approximate average grade in the class? We could say perhaps a B. Now we can also complicate this a little bit by, instead of having histogram with buckets, making a smooth curve and looking at a few different classes. So now I have 3 fake grade distributions. The blue, or the first, the green, which is the middle, and the red, which is the furthest to the right. Let's say all of these classes have the same number of students. What is the average grade in the blue class? We could say maybe about 25. In the green class, maybe about 50. In the red class, maybe about 65. So looking at these 3 classes, which class has the highest grades on average? It's got to be the red class, right? It's a 65 average instead of a 25 or a 50. And looking at these 3 classes' grade distributions, that makes sense. Now I might ask you a bit of a silly question, but it's a very common mistake. The peak on the red graph isn't as high. And yet, the red graph is the one with the highest grades on average. Why is this? Take a second and think about why that question would even exist. We call this a wider distribution. What it means is that there is a wider variety of grades. And so even though there is the exact same number of students and it's a higher average, the peak itself is lower because it's spread out. Some students did very poorly and some students did very well, but in the blue class, everybody got very close to the same. The same is going to be true when we look at the distributions of molecular speeds, and the graphs are going to be very similar, although they're not quite the same distribution as is typical in a graded class. So let's first look at the way that temperature affects speeds. We'll start with what we know. As temperature rises, the speeds of the molecule increases as well. The thing about that we've been saying, well, it's a really, really dramatic oversimplification. One that I alluded to by always saying that it was the average speed that went up. So there's actually this distribution of speeds that look like what I have here. Let's first focus on one of the graphs. Let's take the 100K one. We have a distribution of speeds. As we raise the temperature to 300K, the distribution widens and it gets faster overall. This moves the average speed up to around 400 meters per second. Keep in mind what we did when we did the grade distributions to find the average. You find the middle of the curve and you go down to the x-axis. As with the grade distributions, the reason that the peak gets shorter is that there is a wider distribution of speeds, which means that there are less molecules at each individual speeds. And of course, lastly, the 700 Kelvin graph. That one's even wider and it has a faster average molecular speed, which if you follow the peak down is around 600 meters per second. Now let's do the same thing for masses. If we are at a given temperature and all of our samples are at that given temperature, all of the molecules are going to have the same kinetic energy, which means that if one molecule is heavier than another, then the overall speed of that molecule must be smaller to compensate. We can see, given these distributions, that while we may oversimplify this by saying the bigger the molecule, the smaller the speed, we should take into account that we are still talking about the whole distribution of molecules, and that we're talking about on average. We can see that in the helium graph here. We have a much smaller molecule than chlorine, and has a much faster average molecular speed and a much wider distribution of molecule. Now let's do a quick derivation to solve for the root mean square speed. According to the kinetic molecular theory, the kinetic energy of a mole of molecules is equal to 3/2 RT. Consider that a given. We are not going to go into the derivation of that equation. Now let's consider some things that we know. We know that the kinetic energy is 1/2 mv squared. This means that the kinetic energy for a mole of electrons is Avogadro's number multiplied by 1/2 mv squared. This makes the masses turn into molar masses by doing this, since we have the mass times by the number of moles. Now, since both equations are equal to the kinetic energy of 1 mole of electrons, we can actually set them equal to each other. Now, why would we do this? Well, with a bit of rearranging, you'll see. From here, we are able to solve for the URMS. This gives us an equation that relates the URMS to the temperature and the molecular mass. And we'll use this to solve for the URMS and quite a bit in the effusion section. This equation also helps us to remember the relationship between mass and speed. If we increase the molecular mass, which is in the denominator, then the speed is going to go down. So the larger the molecule, the smaller the speed. Or in other words, they're inversely proportional. Now let's do a couple of examples. Here I ask you to calculate the RMS of helium and nitrogen. We have our equation from our last slide. All we have to do is fill in all of our values. I do need to give you a temperature in order to do this, so we'll do it at 298 Kelvin. From here, we can fill in, well, our 3, which is already there, our R, and notice the units on R in which value I fill in. Now we're talking about energies, masses, and temperatures. And so we're going to use the other unit for R. We're going to use the joules per Kelvin mole value. So we fill in 8.314. We fill in the given value of 298 Kelvin, and we divide by the molar mass. Now note in the molar mass what the units on that are. We had to change it into kilograms per mole. And this might seem counterintuitive because we generally relate molar mass in grams per mole, but remember that joules has a kilogram in it. So when we fill this in, we have to fill it into kilograms. And we get our value. Now we can do the same thing for nitrogen. Take a moment and do that yourself before moving on. For nitrogen, we'll do all the same things, except that we fill in the molecular mass of nitrogen. Remember to multiply the molar mass you find on the periodic table by 2, since it's diatomic, and then divide by 1,000 to get kilograms per mole. From here, we can solve for our final value. Now, this is a problem where we can make sure that our answers make sense in case we made a mistake. Which one of these two is faster? It's the helium. It has over 1,000, while the nitrogen only has 515. Does this make sense? Of course it does. We know that the smaller the molecule, the faster the speeds, and helium is smaller and it has a faster URMS. Let's quickly review. The kinetic energy is the energy of motion. Kinetic molecular theory assumes that all molecules are point masses with random motion and elastic collisions, just like all of our ideal gas work. As temperature increases, so does the average kinetic energy. The higher the speed, the higher the energy collisions with the wall and the more pressure we get. The more molecules we have, the more collisions with the walls and the more pressure that we get. The speeds and/or kinetic energy of the molecules in a sample are a distribution, not simply all ones.